pull it out, and you know this is a disk centered at the origin with radius r. So if I have y simple in this combination, I need two numbers for x lower and upper functions for y, right? And we are pretty smooth about this already. So x, I have minus r and positive r, right? So it's going to be minus r, positive r. Oh, I'm actually using double the same letters. Let's say this r is a region. My capital R here is the radius. Okay, yeah?
Can we turn this into like a polar coordinate?
Exactly. Let's finish that. Let's identify it first and then see what happens in terms of the actual evaluation. Okay? So if I want to identify it as a y simple region, I have a lower function minus square root of r squared minus x squared, because this equation is defined by x squared plus y squared is equal to r squared, right? This is the equation. And upper function is going to be square root of r squared minus x squared. And 2 square root of r squared minus x squared minus y squared dy dx. At least I will be able to identify this region as z simple in the space, y simple on the xy plane. Are you with me? I can also identify this region in any one of the 6 different integrating orders. I should be able to do that. And I highly urge you to do this after class, to practice yourself and get yourself used to how to identify this between 6 different integrating orders. However, in terms of evaluating, as long as I end up with this step, I can in fact, as I said in the beginning, I can in fact forget about I'm dealing with a triple integral. I'm simply evaluating this double integral on a disk, all right? I'm simply evaluating this double integral on a disk. And we discussed this before. If your integrating function contains x squared plus y squared, or your integrating region is a piece of a disk using polar coordinates, is extremely easier. It's much easier than using x and y. So not only I can identify this as a y simple region, I can also identify this as a polar rectangle effect. So let's quickly do that. So if I'm looking at this double integral using a polar coordinate system, theta goes from 0 to 2 pi, and r goes from 0 to capital R, all right? And the inside is going to be 2 square root of r squared minus r squared. This is small r squared, dr, d theta, and something is missing here. R. And r. Okay, so I need an r here. So I need to find the antiderivative function for this thing. Like I said, when you use polar coordinates, most of the cases it's going to get easier, but still you have to do some computation. So here, if you are not very used to the square root, I have 2r squared minus small r squared to 1/2. So I want to find the antiderivative function for this integrating function here. All right? What is the integrating function here? What is the antiderivative function? At least I want to have r squared minus r squared to 3 over 2. All right? At least I want to have this. And then I want to squeeze every factor correct. So if I'm taking the derivative, I'm getting 3 over 2. So I want to have 2 over 3 in the beginning. So I can cancel when I break down the exponent. All right? And then I need to move in by chain rule to multiply by 2r, which is minus 2r right here, right? I have a minus 2r, but I have a plus 2r, which means I have to have a minus sign. Again, if you're not 100% sure about your antiderivative function, what do? You take the derivative. So if I'm looking at this function and I want to take the derivative, what I have here is, first I have 3 divided by 2 pull out, I get a minus r squared minus r squared, and then exponent has to be decreased by 1. It's going to get 1/2, all right? And then I need to multiply the derivative of the inside. Multiply by minus 2r, which is exactly equal to this guy, okay? So taking derivative. Okay, you can always take the derivative to verify whether the antiderivative is correct. And if you do not feel 100% sure, if it is 1%, you doubt yourself, always take the derivative to verify yourself. Because we have this experience, taking derivative is much easier than finding the antiderivative, right? So you can simply take the derivative to verify. It doesn't really take that much. And then I have to evaluate from r is equal to 0 to r is equal to capital R and d theta the outside. So it's from 0 to 2 pi. When r is equal to capital R, this whole thing disappears. When r is equal to 0, I have minus, so 0 minus 2/3 multiplied by r squared, then to 2/3 d theta in the outside, right? So that's what we have. So r squared to 2/3 is exactly r cubed. And then the inside has nothing to do with theta, so it's only a matter of multiply by 2 pi, all right? So it's going to be 2 pi multiplied by 2 divided by 3 r cubed, which is end up with 4 divided by 3 pi r cubed, which is exactly the formula right here. If you can, if any one of you can provide any other alternative proof without using calculus, I will be very happy to hear. Okay, you can try to do that. So the volume of a ball is equal to 4 divided by 3 pi r squared. R here is the radius. So this is an extremely nice application of triple integral. Remember when we did a double integral, we compute the area of a disk, and we actually verify the area formula is pi r squared, right? Here we actually verify the volume of a ball is 4 divided by 3 pi capital R squared. Okay, questions? Okay, now I need to up our games. Okay, so I want to move forward and discuss a couple more examples. But before that, in the very beginning about triple integrals, I didn't mention about our plan. Our plan is to go over, I think, 6 different types of solid regions, right? So the cubes are the most easiest cases. We also talk about z simple, x simple, and y simple. Unfortunately, we don't have that much time to practice too much. So you definitely have to practice afterwards. Okay, so we actually practice against that plane, and also we practice against this ball. But you need to practice more in order to identify the solid region as one of the x, y, and z symbol. We'll also go forward and discuss cylindrical coordinate system and a spherical coordinate system. Cylindrical coordinate system is pretty easy. And actually, we are indeed using the cylindrical coordinate system right here already. In terms of cylindrical coordinate system, we're still using a z variable. And in x, y, we're using polar. That's all. That was me. So here, strictly speaking, we are using cylindrical coordinate system already. We're using polar on x, y, and z keeps as usual. So this is cylindrical coordinate system. Spherical coordinate system is slightly more complicated. But for cylindrical coordinate system, it's just a polar plus z. We already used that. Okay. So I want to actually use this idea one more time, which is actually the cylindrical coordinate system. So I want to find the volume of the solid above z is equal to sort of x squared plus y squared, and below x squared plus y squared plus z squared is equal to 32. Okay? So before I even sketch it, I want to quickly test your quadratic surfaces. What is this? It's definitely not a plane. right? Because for a plane, you have to be all linear. So you have squares. No, if you don't like this square root, is a squared is equal to x squared plus y squared. This is a cone, right? This is actually a cone. A cone is a quadratic equation where you don't have any constant, okay? So this is indeed a cone. Not only it is a cone, but I'm taking the square root, so this is actually the upper half cone, right? This is the upper half cone. What is this guy? This is easier. No, not easy. If you see squares, you definitely not a plane. Right? A plane has to be all linear. This guy is x squared plus y squared plus z squared is equal to 32. It's a sphere, am I right? It's just a sphere. It's a sphere. Maybe I'm scaring you here. So it's just a sphere centered at the origin with radius square root of 32. It's a pretty easy one. We just dealt with that, right? So let's quickly graph these two things. So I have a cone going upwards. And then I have a sphere centered the origin with radius 4 square root of 2. So this is indeed what you're going to get. Okay? One of our favorites. I-squared cone, right? So you have a cone shooting upwards, and then you use this cone to cut through the sphere. So the sphere, the whole sphere is looking like this. And then you use this cone to cut through. This is going to be the I-squared cone, right? So next time you can say, okay, not only I'm buying this I-squared cone, but also I know how much this I-squared may contain, right? By using calculus. Which is exactly the question of computing the volume of the solid, right? Assuming there's no, everything is filled right up in here. Right? So we want to compute, again, when you sketch the surface, when you sketch the region, you don't have to be super precise. You don't have to be super precise. But at least you have to be able to identify something, right? You have to be identify something. For instance, you have to at least know there is intersecting curve between these two surfaces. Are you with me? So if you have a cone shooting upwards, and then you have a sphere bounded, right? You have a sphere which is centered at the origin with radius 4 square root of 2, definitely there's an intersecting curve between these two. All right? This intersecting curve is pretty important. You have to be at least able to tell this from your sketch. You don't have to be very precise otherwise, but you have to at least be able to compute everything. So again, if I want to identify this as a z-simple region, I need a region on xy plane, lower function and upper function for z, and I'm integrating a constant function to 1. I'm simply writing down dx dy, not very seriously here, okay? Because I haven't really identified what the region is on the xy plane yet, right? Depending on what identification I'm getting out of that, I'm going to reorder my dx dy. And I don't even want to use dx dy if it is something nice in polar coordinate system. So I'm just writing this to identify as a z-simple region. So this simple region, I need a lower function. What is the lower function? The lower function has to come from the cone, right? So the lower function here is just a z equals square root of x squared plus y squared. The upper function is coming from the sphere right here, right? But I needed to solve for z coming from this equation, so it's going to be square root of 32 minus x squared minus y squared. Okay? What is more important here, probably, these two are pretty easy information you can tell immediately. Which is more important is how do I identify this region R? How do I identify the region R? I'll give you two ideas to convince yourself how to identify this region on the xy plane. One thing is this is the region on the xy plane the whole solid region is built upon. The other one is probably more fertile. You squeeze everything back onto xy plane and see what you got. So if this is the ice cream cone and you squeeze everything back to the xy plane, what are you getting? This is a disk, which is exactly the region bounded by the intersecting curve. Right? So it is a disk bounded by this intersecting curve. So indeed, I have to identify what this intersecting curve is. But what do we mean by two surfaces are intersecting at a curve? We simply combine them together, right? We simply combine them together. So I'm getting a z is equal to square root of x squared plus y squared, and also x squared plus y squared plus z squared is equal to 32. I need some information about x, y. So combining these two equations, I'm definitely working towards eliminating z variable. All right? I need something for x to y. I'm definitely working towards eliminating z. Right? So z here, plug in the second equation, I'm going to get x squared plus y squared plus another x squared plus y squared is equal to 32. So this is going to be the equation of circle. All right? So the intersecting curve is nothing but a circle. Are you with me? So solving for this intersecting circle is just solving a system of two equations because they're intersecting. And then I need x, y to appear in my equation, so you simply just eliminate z. So this is the intersecting curve, and this disk bounded by x squared plus y squared is equal to 16 is exactly the region on the xy plane. Are you with me? On the xy plane. So even though I'm writing it as dx dy, but as long as I know this is a disk, I'm going to go for polar coordinate system. Right? So if the polar coordinate system is going to be from 0 to 2 pi, from 0 to 4, which is the radius of that circle. And then, if you want, you can simply replace everything in the interior by r and theta without even eliminating z. You can do that as well. So here I'm getting r to square root of 32 minus r squared, all right? So x squared plus y squared is r squared, so this lower function is r. Upper function is 32 minus r squared. And then 1 dz, but I need one more r here, right? Yeah. R dr dz. Okay? So, as I said, we are indeed using the cylindrical coordinate system already. We are actually using the cylindrical coordinate system already. If you have an intervening region, in this case, I can represent it in r, theta, and z variables.